Okay, so let's see if we have any more questions. I had a couple of questions tonight that were interesting. So I think there's some issue about whether these excited electronic state species are ions or not. If we're talking about NO or OH, each of these electronic states, you can think of it as a different species, but it's still electrically neutral. It's not an ion. If I take my nitric oxide and I remove an electron fully, then it's an ion. That's just another species. Each species has its own electronic states. So I could go into Hertzberg and I could say, I want to understand the electronic spectra of nitric oxide ions, NO+, or NO++. And in Hertzberg, I would find the energy level structure, electronic energy level structure of that species. So right now we're talking about neutral species. We could have talked about an ionic species. The process would be the same. But each of these electronic states is the different electronic configuration of that neutral species. If we had done this for OH+, it'd be the same analysis. There'd be a ground state and there'd be excited states. If you add enough electron energy, what happens? It becomes an ion. So each species has an ionization potential. Take argon, and I think it's around 13 electron volts. So if you take a neutral argon ion and you keep adding electron energy, you define different electronic configurations until finally you've added so much energy that the electron's gone. Then it's an ion. We're not talking about ions. We could be talking about ions, but usually they have very low populations because it takes too much energy to remove that electron. If you want to have ions in your combustion gas, you put in a little bit of sodium, a little bit of something that has a low ionization potential. That means that at a modest temperature, there will be a higher number of ions. So this would be chemical thermodynamics. So you probably will have done a calculation where you calculate a given temperature and pressure, the fraction of the O2 that's associated to O. Fraction of the, or you do a problem with some initial fuel and oxygen and you calculate at a given temperature, pressure. What's the composition? Species. You could include in that list, if you want, ionic species. It's just that in most conditions, these numbers would be small. It doesn't mean they're always negligible, but they're small. But each of those species would be treated the same way we're treating them here. So the ions are a completely different electronic configuration, but within any given electronic configuration, that is the neutral species, we follow this process that I'm doing here. I'm going to go through OH. OH is important and complicated. I'm going to spend one lecture kind of going through in gory detail how we would do this. If you were going to measure OH by absorption or by fluorescence, you probably would read somebody else's paper and try to copy it. You wouldn't have to do all this. But it's nice to know where the pioneers, what they had to do to find out which lines they're studying and how they're going to interpret the spectra. So we did this 30 years ago for OH. One of my really good students. Anybody here from Georgia Tech? Okay. Huh? Okay, but anyway, one of my students there is Jerry Seisman. He was a real help to me in doing this work about 30 years ago. Okay, so we're going to do UV absorption of OH. We're going to look at the A to X transition. There's the ground state. It's an X2 pi. There's the first excited. Now, you use a capital letter for the next energy, electronic energy state with the same multiplicity. 2 is the multiplicity. And that name is given for the fact because with this, we have 2 values of omega down here, 3/2 and 1/2. So there's 2 values that's reflected in this 2. So when we go up to the first electronic state that has the same 2s plus 1, that's given the letter capital A. Next one up would be capital B. There are also some states in which this multiplicity changes, and those would be given lowercase letters, A, B, C. So X, A, B, C. That's the lowest amount of energy change, but even that amount of energy change means that the photons have a wavelength of about 300 nanometers, which means 4 electron volts. That's a lot of energy. If you wanted to do this in kind of complete detail, you would end up with something like this. These would be the allowed rotational transitions from a specific value of n, which is an integer, because that's the nuclear in this system. If you picked, and I don't know if you'll be able to see this clearly or not, this n is 13. Here, n is also 13, and it's because of this molecule has two values of j for every n. So for j can be n plus a half and n minus a half. So over here, j is 13 and a half. Over here, j is 12 and a half. So for given n, there's two j's. So these are reflected in these vertical columns of possible energy levels. If you have n of 13 and this j, then we have to keep track of some details. If you have this j, you have to keep track of these details. And now, finally, we have to start paying attention to these pluses and minuses. And that has to do with the fact that the allowed quantum transitions are ones in which you have to change p, the parity. It's either a plus or minus. If you go from a minus, you got to go to a plus. You can't go to a minus. It's just a rule. So if we just kind of accept these rules, it's not too bad. There are three primary, for a given n, and this j, there's three possibilities, P, Q, and R. There's some ones, cross ones, which are basically weak. They're possible, but they're weak. So basically, there's three strong possibilities, and there's three strong possibilities. So for a given n, there's 6 lines. And that's because there are 3 for each j. And at some point, we have to worry about this lambda doubling. There's a C and a D here, so there's this lambda splitting. So this is like the most complicated thing that you'd have to worry about for a diatomic molecule. So now, you have to think about the energy level structure in the upper state and in the lower state, because you're going to take differences. They may have different characteristics that we have to worry about. We're going to have some more notation stuff to worry about, and we're going to do this working example. Let's see, did it not? It did not. Oh, there we go. Okay. So I showed this earlier too. This is a calculation that we would do, and I typically give this as a homework assignment in my lecture course. Of course, they have the benefit of kind of knowing what the answer is. But these would be the positions of the lines, and their strengths would be the height. Strength of the lines at a given condition. This would be at 2,000 Kelvin. Why do the heights of these lines change with temperature? Because we change the Boltzmann distribution. In the end, the line strength depends upon the number density and the absorbing state. So there's the line strength in my units of centimeters to the -2 per atmosphere versus wavelength in nanometers. Now what you'll notice is that the highest ones are called Qs. Oh, this is one of those cases where the Q branch transitions are bigger than the P and the R. Buried down lower here, here's an R, and there's a band head. See, there's some sort of a null gap in here somewhere, and the lines go up in intensity and then they come back. So there's a band head in the R branch, and band head in the other R branch. So this is what we would like to calculate. Remember, to get K nu, what do you need? You need, to get K sub nu, you need a number density in the lower state, and you need an oscillator strength, and you need a line shape function. Since we plotted the line strength, there's no line shape function because we've integrated it over the line. So this is basically, depends on temperature, which determines the Boltzmann fraction, and then the mole fraction. So that seems to be missing here. Should have been here probably. Oh, no, this is per unit number density, so it's probably okay. Uh-oh, here we go. Uh-oh. I hope that doesn't come back. I went for hours and this problem didn't happen in my hotel room. Okay, so we have to talk about the energy levels of the upper. There we go. For some reason, it appears after about an hour. I don't understand why. But now it's probably going to come back several times on me. So we're going to go through by identifying, calculating the energy levels of the upper and the lower, talk about the allowed transitions, introduce the notation, more and more notation. Then I'm going to tell you how we do the oscillator strengths. Remember, we need Boltzmann fractions and we need oscillator strengths. And then we need a line shape function. You really need 3 things. Got to get the Boltzmann fraction, the line shape function, and to get this absorption coefficient, we have to specify these oscillator strengths. And you'll see how we do this now. And then I have to go back into my this happens, 2 steps. Okay. So we always sum up the possibilities, the electronic, the vibrational, and the rotational. They each have quantum numbers. The separation of terms that says they're not coupled is often called the Born-Oppenheimer approximation, which we make all the time. G is always simple. Just tell me omega E and XE, and I know what I need. Those numbers differ in the two different electronic states. So you go into Hertzberg, look at the electronic state, take out omega E and XE. You have the vibration. And you also can look in there and you'll find T sub B and you'll find the B sub B and the alpha. So we're going to look at this particular system now. So if we went into Hertzberg, you would find for the upper state, which is an A2 sigma plus, here's the ground state, X2 pi. So notice that we've now changed lambda from 1 to 0. There's a term energy for the ground state 0. Here's the excited state, that's 32,000 wave numbers. There's omega E, which differs from this omega E. Here's omega XE, differs from this one. OH is a hydride, so it's kind of light on one end and heavy on the other. Whenever you have that situation, you get kind of stranger behavior, different than if we had, say, CO, where the nuclei are similar masses. It's called a hydride. So when you have hydride, you get some stronger effects. Let's look at the upper state. We look at the upper state. So the upper state is a case where we have lambda 0. Remember, it was a sigma state, but S is unequal. So we would call this Hund's case B. And this is the case then where we have two possible values of J for each N. S is a half, because its superscript is a 2. And now we have to talk about the rotational term energies. And remember, there are two possibilities. You have F1 and F2, corresponding to J of N plus a half and J equal to N minus a half. So the spin's a half, and so you have to add it and subtract it. And you just have to remember that F1 is the one where you add, and then it follows. If there were more, then you would keep going down by integers. So this is a Hund's case B upper state. And we have to use this notation to get to the rotational energy. So remember, we're trying to get energy. Electronic, vibrational, rotational. Rotational is all the work. It's the one that's complicated. And we can do the same thing for the lower state. Now the upper state. So this would be the more correct expression. I'll stand over here until it goes crazy again. The upper state is A2 sigma. Now, these are the expressions we would take out of Hertzberg. When you see the D term, just pretend it's not there right now. That's the correction term, distortion terms. So basically, it's B n n plus 1, which you're used to. That's the rotational term written now in terms of n instead of j, because this is the nuclear motion, plus gamma sub En and minus. So that is the spin splitting. The difference between these two, F1 and F2, is mostly just right here. And that difference is gamma times 2n plus 1. So gamma is this spin splitting constant. It's a number. You can look it up. It's about 0.1 for OH. So that splitting between these two states increases with n. So that just tells me that when you give me n, it's not enough. You've got to give me j. So here's j is n plus a half, and here j is n minus a half. And those two states are split. Those two states are split by this amount. And here's what it looks like. So if you tell me n, I have two values of j, 2 plus a half, 2 minus a half. The upper one is the F1, and the lower one is the F2. And so on for j of n of 1. N of 0 is the simpler case because there's only one allowed value of j. Now, I've added here the parity, plus and minus. There are rules for what this parity is. In this case, I know what it is because for even n, for this wave function symmetry, and we could look this up in Hertzberg, the rule is that if it's an even n, it's a plus. So we have n of 2, this is a plus. N of 1, it's a minus, back. So we have to add this notation because it will constrain the ultimate transitions that we can worry about. The ground state. Well, the ground state is different. The ground state has both orbital and spin angular momentum, and it's a Hund's case A. Now, Hund's case A would say that sigma is defined, so we add it right here. Hund's case B would be if it's not defined. And the trouble with the hydride is that it doesn't follow the rules so well. It follows the rules that this should be Hund's case A at low end, but when n goes up, it wants to become uncoupled and become a B. So how do I know this? Well, I read it in Hertzberg, or I read it in journal articles. So unfortunately, hydrides are bad actors. They don't follow the rules very well. And so what happens is that this L, which is that orbital angular momentum, it couples more to the nuclear motions than it does to the spin. So that's the way it is. So when this happens, it's called an intermediate case, and the bottom line is that it leads to more complicated expressions, which I take out of Hertzberg. So it turns out that that's known that by studying spectroscopy in the laboratory, that we can still use this notation F1 and F2, but we have to modify these expressions a little bit. Whenever you see the D's, just pretend like they're not there. But you have to worry about some terms here. And here's this Y term I told you that's the A over B. So we're looking now at this kind of spin-orbit coupling in these modified equations. So the equations get modified, but they're known. So what you're looking for are energy expressions for the energies of the possible states. You take the differences for the allowed transitions, and you get the spectrum. Then you impose Boltzmann statistics to get the number density. You impose the oscillator strengths, and you're done. There's kind of three parts to this. Energy level expression. So for small n, if you look at these expressions, you'll see for small n, neglect these terms here. For small n, and remember A is this ratio of A over B, which is a big number, but it can be negative. So for small n, we throw these terms away, and here's an important point. You'll see that F1n has a minus sign, and this one has a plus sign. What does that mean? That means F1n has lower energy than F2n, and that's meaning that it's inverted. So it's like a Hund's case A when the n is small, but it becomes transitions to case B. So you can look at these equations and see that you recover the A form or the B form depending upon whether n is small. So somebody figured this out. It would not be this bad if it were, except for the fact it's a hydride. So all this means is that for a given n, I can have j is n plus a half and j is n minus a half, but because it's inverted, the 5 halves is actually lower than the 7 halves. Excuse me, 5 halves is higher than the 7 halves. So this is then the F1 set is lower than the F2 set, because we showed this on the previous slide. So what have we got? We have expressions now for the energy levels that depend upon J and N. And we have a physical explanation here in terms of these spin-splitting numbers. And if you study these notes, you would find that we could look at these limits and you can try to interpret these numbers in terms of the model that I introduced. And you would find out that it doesn't quite follow the model. So the model is a model. The reality is the reality. Where do we get the reality? We make measurements in the laboratory, and we figure this out. So there's an explanation for these energy levels. Now one more problem. Because of this lambda doubling problem, that lambda can be pointed either this way or this way, each one of these individual lines is slightly split. So now for a given n, 2 say, there's 2 j's, but each one of those is further split by lambda doubling. So now, what does that mean? For each n, there are 4 states. It's not enough, oh, there we go again. It's not enough to tell me n, you've got to tell me the other information here. I think there's something about time. After about an hour, it seems to want to do this. Let's see if we can get through it. Okay, so keep in mind, one n leads to 4 states. Now we have to get into the transition notation because in a journal article they'll talk about the lines in this form. We're talking about transitions between v double prime in the ground state 2 pi going to v prime of this state. We have to decide what n and j are. And so there's a compact notation right here that I'm going to show you. I should have put a space right here. Here's the compact notation. This would tell me what transition I'm talking about. The y corresponds to delta n using the same alphabet soup we have before. The X corresponds to delta J, so that can be a P, Q, or R. The alpha and the beta tell me whether I'm in F1 or an F2. And then finally, I have to tell you either N or J. For OH, if this is an even number, it must be, an integer, it must be N. If it's a half integer, it must be J, because J is half integer, N plus a half, N minus a half. So for example, if I said I'm studying the SR21 line in the 0, band of this system, that would tell me that from here that delta J is 1, delta N is 2, and that the F prime is upper state, which is the second one, is F2. So it's very dense, but it has all the information. And you just have to work with this and kind of study it. If, as is often the case, delta N is delta J, then you don't see the Y. If alpha equals beta, you just see 1. So oftentimes it looks more compact. It might look like this, R17. Sometimes just R17. So that tells you that R is the delta J, and that delta N is equal to delta J. Tells you that alpha and beta are equal, and the number there is at 7, so that tells me that that's N and not J, because J would have to be 7.5 or 6.5. Now, rules. Parity has to change. Delta J can be 0 or plus or minus 1, and you cannot have a J equals 0 to 0. That's a sub-rule. Now, that is all you need to interpret this very dense-looking diagram. So given N has 2 J's, but each one of these has split by lambda doubling into a C and a D, C and a D. Now here's the upper state. The upper state is simpler. It doesn't have lambda doubling. So there's only single lines up here. So if you kind of work your way through it, if you're in this state, where can you go? You can go up by a P or an R. You can go to here, and you'd find that you've changed parity. Good. You can go from here, you can go to here, you've changed parity. Good. You can't go here. But you could go there from here, because this has a parity of a plus. So you'll see, if you study this, there's only 3 primary possibilities from this N and J. And ditto. So there's 6 strong lines. You would say, well, there's a PQ and an R, there's a PQ and an R. But there's 2 J's for every N. So for a given N, there are 4 states and 6 primary lines, therefore. That's a lot. But in fact, you can study this. The rules are pretty clear. Now let's see, what's this? So these are, they're called satellite branches. They're weak. So, but in a tabulation, you might see that there's 12 lines listed for a given N rather than 6. But 6 of them are really weak, so we'll not worry about those. You have to always honor this rule. You might care about what the spacing is. It tends to be a number like this. So it can be when N is 10, which is a fairly big number, you can get 4 wave numbers. So that's a big enough spacing that the lines are fully separated. If we had been fortunate enough to have a x2 sigma going to a2 sigma, so that we have spin but no orbital angular momentum, life becomes very simple. Forget these weak ones. You just have P, Q, and R. Excuse me, we just have R and P for each of these possibilities. We still have J as N plus or minus a half. So now we're ready to try to do something. We're back to this equation. We want K. We want K so that if we measure the fractional attenuation of the laser beam, we can, over a given length L, we can determine the number density in the absorbing state. We may have to invoke the line shape function if we've used a tunable laser. This term, h nu over kt, that's the energy spacing, which is 300 nanometers. That would be, this term is basically just exactly 1. So it's a constant we haven't specified yet, a line shape function that we calculate depending upon with the Voigt function, but their measurement gives us the number density in the absorbing state. If you want the total number of OH, you have to tell me the temperature so I can invoke the Boltzmann distribution. This is just a number, 0.0265. So really what it boils down to interpret our absorption experiment, once you pick the transition you're going to study, I just have to know the oscillator strength, and I need to know this Boltzmann fraction. I need to know the temperature to evaluate this to eventually end up with the total number density of A, the nth of A. Now, how do we deal with the oscillator strength? We have to have general expressions, but it turns out to be simpler once you do it. The oscillator strength for the transition between the lower state here with the double primes and the upper state with all of its glory is written as the product of three terms. The oscillator strength for the system between the two electronic states, and remember, whenever you see an F, it's a number, it's a fraction. Q is the Frank-Condon factor, it's a fraction. HL is the Hanson factor, it's a fraction. I hope I said that right. F is a number relative to the classical value of the oscillator strength. Q is a fraction, HL is a fraction. So if you're in a given, let's do it the other way around. You're in a given given state of the excited state A, and you watch the spontaneous emission to all the possibilities. All the possibilities. That's characterized by the system oscillator strength, that number. The trouble is, from this state, you're in a specific vibrational level, and you can go to other vibrational levels down here and different rotationals. So, but the sum of all those possibilities is given by the oscillator strength F. This is telling you the fraction that go from one V to another. This is telling you the fraction that go from a specific J to a specific J. So these are fractions. What that means is that if you sum over all the possibilities, if you were in a given, this is written, I'm summing over the upper state. So if I'm in a ground state, V double prime, and I want to sum the Frank-Condon factors to all the possible V primes, they're defined so that the sum is 1. If I want to go from a specific J double prime to a specific J prime and sum over all those possibilities, I get this number here. It looks a little complicated. And this has to do with the lambda doubling. So if we have lambda doubling, there is a 2 here. If there is not lambda doubling, there's a 1 here. And this is basically the multiplicity, that's the spin splitting, times this number. So for our OH, this is a 2 and this is a 2, and so there are 4 multiplied by 4. All of these things are defined in a way that the fractions sum to 1 when you consider all the possibilities. Okay, so, I'm going to skip over this. This is way too complicated. Okay, so where do we get these oscillator strengths? They're measured. They're measured in different ways. They've been being measured for a long time, 1938. Interestingly enough, this guy got it almost exactly right. Because the experimental methodologies have changed. Different people use different strategies. Marshall Lapp also got it quite right. So it looks like there's a lot of variation, but nowadays people would say, see, look at this. People would say that it's really close to 0.001. That would be the accepted value, and we would say that the uncertainty is about 3%. There are ways of measuring it. In any case, there's a body of literature on F00. So what's F00? That's the probability of going from 0 to 0. These are the vibrational numbers. So that's interesting because what they've done, okay, I'm going to go back. They have combined the system oscillator strength and the Frank-Condon factor. So they're immediately giving you the product that you care about. Half of your work is done. So let's see here. This is a pain. They're determined to get me. Okay. So that's, we basically make use of tabulated information. Now, what about the Hanson factors? They're tabulated too. And it'll look something like this. These are the Hanson factors for the different transitions. So let's look at Q13.5. Since there's no superscript, that means the delta n is equal to delta j is +1. It's a Q. Since there's only one subscript, that's telling you that alpha and beta are both 1. Since this is 3.5, that's telling you that that's j is n plus a half. So n is 3, j is 3 halves. It's a Q branch transition, and that's the number. It's a number defined so that the sum of these numbers for all the possible values of J prime will equal to 1 when normalized this way. So it's something you have to study, and what you have to be careful about is that you use the right normalization so everything sums properly. When you do a Boltzmann fraction, you check to see that the sum of your Boltzmann fractions is 1. That's how you check yourself. So this is all defined in a way that adds up properly. So remember, we're only after one oscillator strength, F12, but it's given to us by the product of the system oscillator strength, the Frank-Condon factor, and the Hanson-Linden factor. Sometimes the first two are combined into a table already for you. And then you just go to the Hanson-Linden factor table. So they're tabulated information that you can use to get the system, to get the oscillator strength for your transition. So you decide what line you want to study. You look at the absorption spectrum, decide the line you want to study, and that and specify the N and the J, and you can then get the oscillator strength you need. So let's see, this is just a reminder that if you have a given N, there's 2 J's, but each one of those J's is split by lambda doubling. So there are 4 states for each N. 4 states for each N. I'm going to skip over this. Okay, now we're going to try to do Boltzmann fractions. The vibrational fraction is easy. What's the fractional population in V? Well, we go back to the initial e to the minus energy over kT divided by the partition function for vibration. What happened to G, the degeneracy? It's 1. So for vibration, the degeneracy is 1, and there's no 2J plus 1 there. Q is the sum over states. So the vibrational Boltzmann fraction is easy. It's the rotational one that's tricky. And so now is when you have to invoke a model. And this is the model you would apply to the ground electronic state. What's the Boltzmann fraction for a given V for a specific N? Now it looks like the quantity you've seen for a rigid rotor, except we use N instead of J because we have the electron contributions. So these look really pretty similar. Here's the rotational partition function T over theta R. This is an asymmetric molecule, so you don't have a sigma down there. So again, this looks pretty simple. Where's the problem? The problem now is that we have to recognize that there are 4 substates for every N. It really boils down to that. So if you ask, well, what fraction are in a given J, you're going to get 1/2. So for a given N, half are in one J and half are in the other. Now you have to say what fraction are in a given lambda double state. You get another half. So a given N is divided into 4 substates. And you can just keep checking yourself on this. Okay, so if you put all of this together, we need the Boltzmann fraction in the absorbing state, 1. And it's the product of Boltzmann fractions, and it'll look like this, which is really familiar looking. This is the one that's tricky. But the bottom line is, you know in advance, the fraction in a given state is just 1/4 of what you would have gotten if you'd taken a rigid rotor. So you have to always sum these things so that you get 1. Okay, now, do I have time to do this? Let's see. I think I do. Nowadays, we would use a narrowband laser, which means that we would bring in the line shape function. Before the laser was invented, and maybe even after the laser was invented, people sometimes did broadband absorption. I keep telling you that the Beer's law is only for monochromatic light. So what's happening? So let's see, I think I'll just show you the example. If you do narrowband absorption, then you bring in the line shape function. So we have the fractional transmission, and we have to have this line shape function. So remember, K is S phi. We do the S the way we've just been doing it, but eventually we have to impose a line shape function. But what happens if you have a broad laser? So if the actual absorption line is this one right here, I could probe it with a laser and I'd scan across and I would map out that absorption line. But what if I have a light source that's spectrally broad? What if I have a light source that's broader than my absorption line? Some of the light in the wings does not get absorbed. So the fraction of the attenuation is a reduced fraction. And so how did people deal with that? They introduced the concept called equivalent width. I'm just going to expose you to this to remind you. Life is simpler if you have a monochromatic source. If you have a broad laser source, or maybe a continuum lamp or a xenon lamp or something, you have to deal with the fact that there's an instrument broadening, that there's an effective width of your instrumentation that distorts the line shape that you measure. And that's usually done by saying, well, there's an equivalent width for my absorption. So there is a way to deal with this. And it results in something that's similar to the Voigt function, the equation of which I didn't have on my slides. It looks something like this. And this is presented in the literature in the form of curve of growth. So if you have a broad light source, and you therefore don't have Beer's law, you have to do an integral. And when you do that integral, you have to involve both the width of the line and the width of your light source. And you get so-called curves of growth that you have to interpret. Not so clean. So you can see, when would you do this? When you have a spectrally broad laser, or you have a spectrally, if you're looking maybe with an instrument that's got instrument broadening, just remember, you can't use Beer's law. You have to do an integral of some kind. Okay. I'm going to do an example calculation in 15 minutes. So let's say you look in the literature and you realized that the strongest line in the 0-0 system of the X to A, of the 0-0 band of the X to A system is the Q19 line. Because you looked at that diagram that I showed you earlier and you saw the Q's are higher than the P's and the R's. So you'd like to evaluate this. And you look in a table and you find out the wavelength is 309.7 or 6, frequency is 32,000 wave numbers. You'd like to do this at, say, 2,000 degrees. Maybe you looked at some collision broadening and you found out that the collision broadening of that condition is about 0.05 wave numbers. So we'd like to express the frequency, the absorption coefficient as a function of the partial pressure, so that we could determine from an absorption measurement the partial pressure, or the pressure of the OH. Well, here's our expression, K. Remember, everything comes down to K. I can do emission or absorption with K. It's a number. Here's my units. Here's a number. The partial pressure of A, which is the number density of A, times the Boltzmann fraction in this state. Boltzmann fraction, the number in this state divided by the total number of A. I need an oscillator strength for that specific transition, which is usually written as F, J prime, J prime, and I need a line shape function. So I've invoked this P equals NKT here to write the number density of the number density of the species. So it's here and here. This is just the number in the absorbing state. Okay, so there's really only three parts to this. I need the oscillator strength, I need the line shape function, and I need the Boltzmann fraction. It comes down to that. I go into some tables and I find out, well, this QF, the oscillator strength for Q19 is the value for the specific vibrational transition times the Hanson-Linden factor. And if you went into the tables that I had, you would find that that is the oscillator strength F is 0.001. Remember, that's kind of like, I told you the best value was 0.001 for the system oscillator strength. Now we're using 0.0096. This is the number that appeared in the Hanson-Linden table. I'm done. That's the oscillator strength for this transition. Line shape. You know how to do line shape. Yeah, there. With that, we go to the Voigt function. So you need to know a little bit about, you have to know the temperature, which gives you the Doppler broadening. You'll have the temperature 7.17, 10 to the minus 7, nu 0, square root of T over M. Okay, now I'm getting something here. What happened? Interesting. Let's try this here. Okay, so let's see if I go backwards now. So I have to get my line shape function, and so I evaluate the Doppler width, from which I use the temperature, the molecular weight, and the wavelength, or frequency. Done. I do the collision broadening, from which I need 2 gamma. I need the collision broadening coefficient for that mixture. Done. That allows me to evaluate the Voigt parameter A, and go into the Voigt tables and get my line shape function at line center. Done. So I want K. I've got this number now. I've got this number now. I have to worry about this Boltzmann fraction for this given state, this one. The way to think about it is the product of the electronic fraction, the vibrational fraction, and the rotational fraction. And so I divided it into parts. And so the way this is summed is you have to multiply these things together, and you end up with a number. And if you're worried about this, you would say my Boltzmann fraction should be essentially 1/4 of what I would have gotten with the rigid rotor. So I've got an oscillator, I've got a Boltzmann fraction now at this temperature, and I evaluate it, and that's the number, 177 centimeters minus 1 per atmosphere times the partial pressure. So if I made a measurement of K by measuring I over I0, take the negative log, take the length, I solve for K nu. I know K nu has to be this number, and with this constant, I've just found the partial pressure of OH. And because this is a big number, that means I can actually measure pretty small numbers. So with Beer's law, this situation, I would correspond to 59% absorption if the length were 5 centimeters and the mole fraction was 1,000 ppm. So if you know the temperature and you know the path length, and you can calculate the Doppler and collision broadening, and you use the equations I've given you, you've just measured the total number density of OH, which if you knew the pressure, you would say that's a mole fraction. So you can use this to determine the temperature, or you can use this to determine the number density. But for this absorption measurement, I need to know length L, and I need to make this calculation. So even though the background theory is pretty dense, in the end, it boils down to 3 things I have to do. Line shape, oscillator strength, which I really get from tables if I went the specific wavelength, and this Boltzmann fraction, which looks kind of dense, but in fact, if you remember that it's just Boltzmann fraction, and you're going to get a number that's like a rigid rotor number divided by 4. And that would lead me to this plot. So with that background, I could calculate this plot. For a given temperature of 2,000 Kelvin, I could plot the line straight. So you can see now why they wanted to do Q1 of 9. That's the strongest one. Now, let's see, there would be band heads. So you always have band heads. Here's a band head. There's actually 2 band heads. They're both in the R branches. Remember, we have 2 R branches. 2 R branches because we have the spin splitting. Why do we have a band head? We have a band head because when you look at the rotational energies, you see that one of the terms is B prime minus B double prime. So it's when you have different values of B in the upper state and the lower state, you get band heads. We didn't see band heads in row vibration because the upper state B and the lower state B for vibrational transitions is very close. But for electronic systems where you have big differences in the minimum position of the potential energy well, you can get very band heads at low J. So we're a little ahead of schedule, so we have some questions. This now brings us to a place where we stop talking quite so much about theory, and we try to start looking at some example applications. So what I was trying to show you is, well, the theory looks kind of dense, but if you boil it down to certain situations, it's not that bad. And now we can begin to show the power of doing laser techniques. And I'm going to talk first, I think I'll spend 2 lectures on tunable diode laser absorption spectroscopy and something about lasers and detectors and fibers. So there'll be some fundamentals, and then in the next lecture I'm going to talk about aeropropulsion. Then the first lecture tomorrow will be applications to combustion energy. I think that's right, yeah. Okay, so any questions? Yes?
Previous slide, is there a band head in Q branches?
Let's see. Yes, I think so. Let's see. Here's the Q2. Now remember, in the limit that there's no difference between B prime and B double prime, all the Q lines are at the same place. But in every other case, then there can be a band head. The can has to do with the fact that it might occur at high enough J that there's too little population for you to see. But yeah, in principle, there will be a band head, but yeah. So that's important because you might say, well, I want to be at Q19. Why do I want to be at Q19? Well, because there's no other lines in the vicinity. Nice clean experiment. So sometimes you look to find a place that has the biggest line strength, but also where there's freedom of interference from other species or other transitions. Good question. Yeah. Anything else? Well, we're 5 or 6, 7 minutes ahead of schedule. I think we don't resume until 11:15. Okay, thank you.